Hello, welcome to Basics of Finite Element Analysis Part 2. Yesterday and day before yesterday, we have been discussing different types of errors which exist in finite element solutions, and also how these errors can be measured and quantified in terms of a single number. Today what we are going to discuss is that how do finite element solutions converge, that is they become closer to the exact solution, and on what parameters they depend, and to what extent they depend on these parameters. So, our theme for today is convergence. Okay. So first I will give you some brief idea what is convergence. So, if I have a finite element solution and with 5 elements, it will have some difference with respect to the exact solution. If I use the same approximation functions, but double the number of elements, the error will go down. If I make the number of elements 4 times, error will go down further. And as I keep on making my finite element solution, so as I keep on increasing the number of elements and keep on making my solution more and more accurate, the error reduces, and this process of reduction of errors is designated as convergence, because our finite element solution is slowly or fastly, depends on how good our algorithm and approximations are, but essentially the finite element solution is converging towards the actual solution. So, this process of convergence of finite element solution towards the exact solution is known as convergence. Whenever we do finite element analysis for any problem, we have to make sure that our solution has converged. It is important to understand that, and what that means is that once the solution has converged, then we can be reasonably sure that our solution is fairly close to the exact solution. If we are not sure whether the solution has converged, then we cannot rely on those finite element solutions, because we do not know whether those finite element solutions will reflect the reality or not. So, that is why convergence is important. Now, in a mathematical sense, the solution u h of x is said to have converged. So, it is said to have converged. It is said to have converged when the norm u minus u h m. So, this is the max norm, and we have already defined what this max norm is. So, the definition of max norm is given here. Oh, I am sorry, this is the energy norm, sorry. So, the definition of energy norm is given here. So, when this norm is less than a number C h to the power of p, and here C is a constant and it does not depend on u or u h. H, it depends on element size. So, it may need not be the exact element size, because you may have a mesh with all sorts of element sizes, but it depends on the element size. Okay. So, overall if your element size is small, then h is small, and so on and so forth. Okay. And P is known as rate of convergence. and it depends on two things. It depends on order of differential equation and it also depends on power of or degree of polynomial function. So, it depends on degree of polynomial approximation function. So, if you use a linear function, it may have some value. If you use quadratic function, it may have, but so it depends on these two, order of differential equation and degree of polynomial approximation functions. Okay. And we will see these things a little bit more in detail, maybe later tomorrow or day after tomorrow. But at this stage it is important to understand that convergence is said to have happened when the energy norm is less than equal C times h to the power of p. Okay. Now what this shows is that I can ensure convergence either by playing with h, right, or by playing with p. So we can achieve convergence either through reducing h, that is making our element sizes smaller, or increasing p or increasing p. Okay. What does h, when I reduce h, what happens? The element size becomes smaller, so my domain approximation error starts shrinking, and also if a function is, if a variable is changing in a very complicated way over the domain, if h has gone down, then it will more accurately capture that variation, right. Even if it is a linear function, it will more accurately capture that variation. So that is how h, by reducing h, we can make the convergence faster by having more number of elements. When I increase p, it means that the degree of approximation function has gone up, which means complicated variation of variables over the domain are accurately captured. So that also makes our convergence faster. So the process of convergence of the solution is of two types. One is H convergence. Okay. So in a lot of literature they say, oh, this is a H converged solution, which means that convergence was obtained by reducing the element size progressively. So you start with 10 elements, then you do 20 elements, and you find that the difference in solutions, because you do not know the exact solution, that is why you are solving the problem. So how do you achieve H convergence? Let us say you have a domain, you break it up into 10 elements and you find a solution. Then you break it up into 20 elements, you again find the solution, and find the difference between those two solutions. Find the difference maybe by finding out this energy norm. So for 20 element solution and 10 element solution, let us say that difference is 10%. Then you go to 40 elements. Let us say the difference becomes 0.5%. Then you go to 50 elements. Maybe the difference goes down to 0.1%. And if you think now that the differences are not changing, increasing, difference is very small, then you say that your solution has converged. So in this approach, you got convergence by reducing the element size progressively. So this is called H convergence. And then you have P convergence. where the number of elements is not changing, but what you are doing is that you are gradually increasing the degree of the polynomial approximation function. So, you start with elements which may be linear in nature, then you go to quadratic elements, then you go to cubic elements, maybe then you go to quartic elements, fifth order elements, sixth order elements, and so on and so forth. So, here the mesh is not changing, the discretization of the domain does not change but what is changing is the the value of p by increasing the degree of polynomial approximation functions. So, that is there. In reality, we tend to do sometimes both, we increase h and we also increase p, we can have a mixture, but these are two fundamental approaches of convergence, h convergence and p convergence. As we discuss this further, I would like to say that there is one inherent advantage if we go for p convergence compared to h convergence, and the reason for that is I will explain that. So, suppose I have a complicated shape, right, and I discretize it. So, the first step is discretize, and then the second step is assume approximation functions, right. When we actually conduct finite element analysis, and if you are already doing that, you would already know, we spend a lot of time in discretizing the domain. We spend a lot of time in generating the mesh, because we have to make sure that the mesh is accurate. There are no elements which have extreme aspect ratios, and there are several other criteria. We will probably discuss that in subsequent weeks. So, a lot of time, and by time I mean man hours, it is not computer hours, because once you submit to the computer, computer keeps on running, then the human labor is not invested, but a lot of labor is invested in meshing the geometry, and for sometimes complex assemblies it can take days or even 3, 4, 5, 6 weeks just to mesh the geometry and to get a very good nice mesh. Okay. So, a lot of this may require lot of man hours. And then once the thing has been discretized, then we can assume approximation functions and assign them and start the solution process. So, all the other subsequent other steps, these do not require many man hours, do not require significant man hours. Okay. So, if we have to ensure that the system is to converge, maybe we initially discretize it into 100,000 elements, then we discretize it into 20,000, 2 lakh elements, then 3 lakh elements, and each time we are discretizing it, we are investing a lot of man hours, right. We are investing a lot of man hours. This is, in other steps the computer takes care of it, so we do not bother too much. The only thing which concerns us that we should not be just waiting for the results for weeks or months, okay. But the computer is doing our job, so labor is not lost. So, if I have to do H convergence, each time I have to mesh it again, and that requires a lot of man hours. If I have to do P convergence, I can mesh it once, make sure that the mesh is working correctly, and then all what I am doing is I am increasing the order of elements, right, order of polynomial functions, and that takes care of the convergence. So, because of that reason, a lot of, in several cases, H convergence approach requires much more human time compared to P convergence approach. And because of the same reason, P convergence approach can be automated, because once you have a mesh, all you have to do is just keep on increasing the thing. But in H convergence, human approach, human intervention is required repeatedly. So that is why this sometimes may be faster. But we will see that a lot of times it becomes impractical to go to elements which are more than 4th order or 5th order, right. It sometimes it becomes impractical to go to 6th order element, 7th order element, 8th order element. So, but from a conceptual standpoint, this may be faster, but from practical standpoint, you can not go for P conversion, maybe not beyond 4th or 5th order elements. So this is something important to understand. So the next thing in this context we will discuss is accuracy of the solution. Accuracy of the solution. So what we are specifically interested in is that when we say that how accurate our solution is, I mean we can measure the accuracy in terms of all these norms, right, max norm, energy norm, L2 norm, but we are also interested in figuring out that when I have a finite element analysis, so let us say this is number of elements and so suppose I have a bar and I am applying some force here, I am also applying some traction here, and I am interested in finding u at this point, at point P. So the exact solution is this u, and this is u at point P. So in this case we are not computing u at different points, but we are interested in finding the value of u at point P. So the exact solution does not depend on number of elements, so it is a constant line, right. So here we are plotting u at point P and UH at point P. Okay. And then what we will find is that when I compute UH, let us say this is number of elements is 10, this is 20, this is 30, I will find that these are the values of UP. So whatever points are there, they represent values of UP. Of UHP, that is they represent the FEA solutions when number of elements was 10, when number of elements was 20, when number of elements was 30, when number of elements was 40, and so on and so forth. Now you will see that I have drawn all these values, they are below this U line, below the theoretical line. Okay. People can think that the solution can come from top also, and it can converge from this direction also, right. But in reality, in a very large number of cases, you will see that the solution converges from below for displacement, and for energy it converges from above. If I am plotting displacement, then it converges from below. If I am plotting displacement, then it converges from above. Okay. So we will try to understand why this is happening. We will try to understand why this is happening. Essentially what we are saying here is that FEA solutions it under predicts displacement. Okay. So, most of the cases, lot of cases, when you are trying to predict displacement, the theoretical value will be more than the FEA value. It will be more than the FEA value. But as you keep on increasing the number of elements, the FEA value will approach that theoretical value. And the FEA solution over predicts energy. So, if you are trying to compute the overall energy in the system, FEA will give you higher energy, a little bit higher energy, and it also over predicts stiffness. Okay. It over predicts stiffness. So, what we will try to understand in next several lectures is what is the mathematical reason, I mean some basis for understanding this. So, that is what we are going to explore. Kitna time hai? So, that's what's going to be the focus of our lectures in next 2-3 lectures, that why does FEA under predict U or displacements, why does it over predict energy, and why does it over predict stiffness. This is what we are going to discuss. So, with this we will close the discussion for today, and we look forward to meeting you tomorrow. Thanks.